So it's my great pleasure to introduce Vincent. He's an associate professor at the Department of Computer Science in the Oxford University. Previously, he was a permanent researcher at India from 2015 to 2023. And he has been also the maintainer of ProVerif, and he will introduce us and give us hand-on tutorial on ProVerif. Welcome.
Hello, everyone. Thanks for the invitation. Great to see so many people. So the goal of today, because I have 2 hours, so I have quite a lot of time, is trying to give you a practical idea how to use ProVerif. For first, really, if you've never used ProVerif before, so we're going to start slowly. And after this, for those that are a bit more used to the tool, some trick tips on how to make it work and how to, what I consider the way I model my own protocol when I study a protocol like TLS or signals. So I'm going to start by giving you some context of where the tools is in the landscape of cryptographic protocols. So we're going to start after this with very standard, from like very toy example, academic example like the Cycle protocol. And then after this, I will give you a glimpse on, I'm not going to say real protocol because the Cycle was a real protocol, but something more recent, the signal protocol with the double ratchets. So something that is actually done in practice, to show you that even though it's more complicated, there's not that much gap into going from toy example to doing something in practice. Okay, so just a quick, who has never heard of ProVerif? Or okay, good, at least 1 and 2, perfect. 3, okay, great. And who has used it once in their life? Perfect, so the first hour will be useful. Okay, so as you all know, we can see there is a many cryptographic protocol that we use in many different area. And here we give small examples. And so usually in terms of harmonization, we consider them as small concurrent program, although now they're not that small, that use cryptographic primitives like encryption, digital signature, and so on and so forth. And each of those cryptographic protocols are, of course, different, but they also satisfy different kind of security properties. So when you think of modeling the protocol, you also need to understand what kind of security property you wish to verify. So the more classical one are the authentication, secrecy, forward secrecy, that kind of like the historical, especially authentication secrecy. Forward secrecy is more recent. And so this, you have a lot of literature in the how to model those security property, and most of the tools are able to handle those correctly or efficiently. You have something that is less traditional, even though now with privacy privacy concern, properties like anonymity and linkability has for a long time have been quite difficult to model, especially not necessarily to model, but to verify using tools. And you also have like new emerging properties that are due to the specific application, like if you think of cryptocurrency, the non-malleability of coins or the balance property are definitely things that before cryptocurrency, we didn't see this in the literature. And in the electronic voting system, I usually like, even though this is a bit older than cryptocurrency, I like to put them because in most of the voting systems, because that's the core of democracy, there's a huge list of security properties to be verified, and there's always a lot of debate on how just to model them correctly. So here we're not really thinking too much on how to model them practically. This is, okay, how do we verify those inside the tool? So, of course, when we think of making a system secure, there's several aspects. So there's the hardware in which you run it. I'm thinking mostly a lot of electronic voting systems, you know, with those machines, for instance, but even the secure chips inside your hardware or your phone. You have the cryptographic primitives themselves that you rely, of course, if you use an old hash functions, it's not going to work very well. So there's a lot of work on this, how to make it secure. But there's also the protocol level. Basically, how do you use, once you have secured the hardware and the primitives, how do you use them correctly? That's kind of the more high level, I consider hardware primitive, lower level layer of verifications. And already at the protocol level, there's a bunch of attacks that you can find, but also on the primitive, and this is definitely not an exhaustive list. I always like to, although I never listed the full list, but I remember a talk, I never remember who gave the talk, of the number of attacks that existed on TLS. And it was very fun because it was put in timeline with every time an attack was discovered, and between each point there was always a paper that was proving the security of TLS. It shows that between each proof there is always an attack, which is kind of strange, but it's not that the proof were wrong, just that the model that were considered were not powerful enough to capture all those attacks. But that always made me laugh. So ProVerif is on the protocol level. And really the idea is we want to have an automated way to guarantee the absence of logical attacks. So we're gonna assume, for instance, the cryptographic primitives are perfect, so the attacker is not gonna be able to brute force. It's really just we're giving what it's supposed to be able to use, and can it do something with this? And the good thing is that, of course, if you have a proof in ProVerif the same way there is this problem with TLS and the multiple attacks between each proofs, it doesn't mean that if you have a proof, doesn't mean that you have a full guarantee on security on the protocol. It's just that you remove a very large class of attacks. So always, and when you do a model, there's always abstraction that occurs, and part of the work is to understand what are the abstraction, what are potentially our weak points. Okay, so even within those, so if you had a bit of knowledge on this, is usually in the literature it can be sometimes confusing because they talk about computational models, sometimes symbolic models, and there are really two different kind of models that usually do not mix well together. And they differ basically on those 5 categories. Is that so in computational model, the real algorithm, or at least as close as possible. In particular, for instance, the messages are really the bit strings that you consider, the 0 and 1. Whether on the side of symbolic model, we are trying to abstract away, especially the primitives, and so we will assume that they are perfect. No attacks possible. No hash function is the one-way function. That's it. And so we will represent them with function symbols. I'm going to delve into this a bit, especially when message doesn't have become a term. So I'm going to talk a bit more about those terms. So within this context, the attacker is somehow idealized. It's not completely, it's not nice, but it's not as powerful in the computational model, when the computational model is still polynomial probabilistic Turing machine. So it's very powerful. But of course, the problem is that those models in the computational model, the proof are much harder. They're usually done by hand. Or recently, there is tools that exist, but they are not automated tools. They are more assistant prover. So you basically need to somehow help him to do the proof. So it needs to be a bit more knowledge. So I would say so ProVerif basically is in this symbolic model. If I were to verify a protocol, I use the good ways to start with a symbolic model because it's really more abstract, but the good thing is more automated, so it's easier to obtain a proof, which already discards you a lot of attacks. And once you have a proof in your symbolic model, you can try to make it work in the computational model, but of course it's much more work behind it. Okay, so although I gave you kind of a symbolic model, it's very nice and everything. And the attacker is idealized, but it's not that nice in the sense that it can still control the full network, so it can read and write on every public channels, or it can intercept messages that you're sending, and of course it can also modify the message depending on what we give him as a tool. But as I mentioned, it cannot break cryptography or use side channel attacks. So basically, this kind of symbolic models, or otherwise known as the model, were created in the 80s. So at the beginning, we were basically working with the toy example we're going to look at. But since then, we've done quite a lot of progress. And here it's a very, what is this talking? There's a lot of actual real protocols that have been verified using those tools, signals, the voting system, TLS 1.3 with an encrypted clienteler extension, WireGuard, and so on and so forth. Of course, again, even though those were proved, always the question is, how did they model the protocol? Because if the tool were kind of older, they made more abstraction. And so if you look at the model themselves, then suddenly you can see that the model maybe could be improved. So usually it's good to go back to your old model and see, okay, what did we do and how can we make them a bit more safer? Okay, so okay, so now let's actually start into the ProVerif part. So that was the introduction to give you a bit of context. And now, how do we model a protocol? And what I mean by this is that if you're lucky, when you have a protocol, you have something like this. This is the good side, when actually everything is correctly written, almost. And in that saying, you really see the flow of message, well detailed, something like this. But already, so you kind of want to translate this into something inside your tool. And when you have this, when someone gives me this to verify, I'm happy. There was some protocol where it was really all written in English, and you have to interpret what the designer of the protocol wanted to do, and this is kind of the bad part. Okay, but first, I told you that we had this notion of term and function symbol. What do you mean by this? Well, so in the symbolic models, we abstract a lot of things. And one of the first things that we abstract is the generation of random number and, for instance, keys. So when we say, oh, let's generate random numbers, that we use this as a commitment. In the symbolic model, we consider this notion of nonces or names, which is basically just atomic elements. So syntactically, it's just, you can think of it as just a letter. So we have variables, of course, to represent, for example, when you're waiting for a message on a channel. And all the cryptographic primitives are expressed using those symbols. So here, the numbers are the number of arguments that your function symbol takes. So here, for example, you could say, okay, I'm going to take one function symbol to represent the encryption, one function symbol for the decryption, so on and so forth. And in terms, it's just basically, it doesn't express what is the actual value, for example, here of an encryption of X by Y, or let's say the X and Y are actual, not variable, but actual name. But you expressed how the message was formed. Okay. So if you're a bit more in the formal theoretical computer science, you can think of it as really just a tree where each internal node are labeled by a function symbol that has the arguments, and subtrees are the argument that you give into your function. So here that would be the encryption with a key K of the plain text that is basically XORing between B and the pair of X. So here you can see that we abstract a lot of things, because when we XOR, we don't have, normally you XOR basically two bit string of same size, otherwise what is exactly a slow, or so you don't have those kind of information here. And what is the pair, what is the pair versus a nonce? So here, that's why we are really expressing how the message was formed and not how what is exactly the value of the encryption, because we don't even know, we're abstracting what is the algorithm that we're using to encrypt. Okay, so once you have this, let's look. How do you use it? No, it's not that. Yes. Okay. It's a bit small. Can you see it like this or more like this? Good. Okay. Now imagine that you have a protocol. So I'm starting with, so it's the link cycle protocol, where, you know, the Alice and Bob representation that I showed you, let's say that you have this informal description where you say, okay, in this protocol, we're going to use the signature algorithm. So it's a signature of you with a signing key S key. I'm going to represent it with this. You have a public encryption of you with some public key PK of A. So let's informally interpret it like this. And we also have a symmetric encryption of you with a key K, represented this way here. And the protocol is very simple. It's just basically a small handshake where A sends a fresh key K that wants to share with B. He encrypts it with the key of public key of B, signs it, and then B decrypts it, check the signature, and starts exchanging with some secret S, some secret S to Alice. Okay, so that would be the informal representation. So, and in a ProVerif model, it's usually divided into different states, I would say. The first is, you're going to see that type declaration. So type in ProVerif are basically here to help you syntactically to make sure that your model is like in, you know, to make sure that your model is correct. So you can type the value of message, so that there's this type checker in the front end. But of course, the attacker is assumed to be untyped, so in terms of verification, all the types are removed. Then you have the declaration of function, equation theory. I'm going to talk about this. And then there's other category that we'll mention later. Okay, so the types, basically what you can declare your own type. So there's no fixed type except two, which is bit string and channels. So bit string intuitively represents any the message of the type of every messages, and the channel is where we're going to send the messages over the network. So here I decided to consider a type. So you have this keyword key. Always everything's finished with a dot in ProVerif. So you have, let's say, a type for the key, so symmetric key, a type for the secret key for the encryption and decryption, asymmetric one. You have the type for the public key, another type for the signing keys, and a type for the verification keys. Okay? So it's here to really, and it's really just you could avoid all the type and put bit string everywhere. That will also work in terms of verification. It's just it's more error prone when you write your own model. Okay, and when you declare a function, well, it's just this keyword fun that tells you basically the function that you declare. Since in the front end we have type, then you also specify the type of your arguments and the type of the output that your function should produce. So here I'm just saying that, okay, S encrypt, the symmetric encryption, takes the plain text here, takes a key, and let's say here I return a bit string. Okay, and you have the same for the public key encryption, public key decryption, and so on and so forth. Okay. I forgot to say, but please feel free to interrupt me. It's supposed to be a tutorial, so if you have any questions, yeah, go ahead.
From your experience, would you say it would make sense to also define types like plain text and ciphertext, for instance, for your symmetric encryption decryption functions?
Yes, you can. Yeah, in fact, that was one I put it somewhere in another way forward. But for example, here it says, to make sure I added another type where I put a cipher as type. So right now the type system of ProVerif is really very simple. It's basically when you declare a type, elements of types are completely different. Okay, so if you declare something of type key, it will be different from any other type, even the type bit string. And the way you can move from one type to another is to, for example, declare to say, let's say, key to bit string. And you say this takes a key, this takes a bit string, and of course this is just for type checking. So, and here you can say type converter, and that allows you basically to magically cast your type. But in terms of protocol, when ProVerif takes this as input, it just removes this function that is just there for the type checking. In a future, let's say soon, I would say within a year, I hope, we will enhance the type system where you will be able to do some orders between types, saying that bit string is the super type, and then you could say every type are subtype of bit string, and then you can refine the types and so forth, so that you don't have to have this kind of type converter. Okay. Good. So, but now what we have those type is good, but if we have those functions, if we never compute the value, what kind of test can we do? So, yeah, as I mentioned, so if the function are abstracted and we don't actually compute the message, so we don't know their value because we abstracted the primitives, the only test that we can perform, basically, this is kind of a simplification, is basically equality between terms. So in some cases like this, it's okay, but in some cases, it's not really okay. For example, here, if we look at the two terms A and B that were just two random nouns generated, it makes sense that in terms of, when we say equality, that would be just the same tree. This is, it makes sense that A should be different from B because there are two different letters, and it means that, I ran twice my random generator, so I should normally obtain two different numbers. So we assume, for example, that in that case that you're not sampling over, over very small. But we assume that you're sampling over your very large space, like the size of your security parameter, and not, you're not sampling over between 0 and 1. So that would be okay. But of course, here, I'll pose those two terms here. That would be, let's say, if you have a term that says it's a decryption of the encryption of the plaintext M with the key K by the same key K, if we just consider equality of terms, pure like this, then it's different from K. It's not the same tree. But that's not okay, because normally, in fact, this is not enough, because you would want to have that if you decrypt the cipher and with the correct key, you should get that it is equal to the plaintext. Okay. So the way we solve this problem, this has been done since the beginning, is to represent the algebraic properties of your primitives using, let's say, equational theories. Okay. So basically, an equational theories is just an equality between term, or you could say a pair of, yes, question?
Just to make sure on the previous slides, that should be unequal to M in the...
Oh, yeah, sorry, typo. Yeah, typo, exactly. It should be, here it should be different from M, not from K. My bad. Yeah, there probably is on the typo in there. I introduced this typo just to see if you find it. Okay, so here there's no typo here. We have X, that's good. So the equation theory are here to express basically how terms should be equal. So for instance, here it says, if you have a term that is an instance of the term on the left, then it will be equal to this, the term on the right. It could be equal to the term on the right. It will be equal to the term on the right, which expresses exactly what we want. For example, here you would say, also if you have a function that does a projection of a pair, you would say, if I try to project the first projection of a pair of xy, it should be equal to the term x. Okay? And you can have much more complex equations. So here I just give you kind of a standard one, but you have the equation of the XOR, which is associative, commutative, with the cancellation as well as the neutral element. But you can also have the group exponentiation with G to do some DPLman, which is how basically we represent it in ProVerif. But you can have even more complicated if you really want to express the multiplicity of the exponentiation with the plus. Okay. So you can express a lot of things with exponential theory. Of course, ProVerif is not able to do all of them. And so basically what happened internally is that ProVerif, you will put the equational theory that you want. I will show you how. And then there's a pre-processing. ProVerif does some pre-processing to try to see if he's able to handle the equational theory that you gave him. And right now, if he's able, he will terminate, right? If he's not able, he will probably just loop indefinitely. So without basically stop. So right now, we don't have a detection of cycle for equational theory, but that's something we'd like to add in the future. And we are working to make that better. So just to give you a quick, very small example of how we use the equation theory with the deduction, because we want, for example, standard secrecy property, standard security properties to understand whether or not an attacker is able to deduce some message. So let's say that the attacker, so we have the XOR equation theory. Let's say that the attacker received those three messages. So XOR of A by B by C, another nonce B and a nonce C. And you would like, for example, to ask ProVerif whether or not the attacker is able to deduce A. And here, internally, the way it works formally is that you can think of it as basically a proof system where the leaves are the messages that he received. And then each line is either an application of a function symbol, because the attacker can apply the function symbol that we give him, and or equality between related to the equation theory. So here, those two messages, A and this guy, those two here, are indeed equal to the equation theory. If you combine those different rules, you will be able to show the equality. Is it fine, this? Okay. So how do we model this in ProVerif? Yeah. Yep. Okay. So first way of or maybe we'll start with this one. First way of doing is just we can add, well, a line here, which is just tell you with the equation, with the keyword equation, that tells you, you just say, okay, for all, and you put the type, and you always have to put the type on the count. So for all bit string X, for all key K, you indicate that it should, the decryption of the encryption with XK by K should be equal to X. And you can do the same for symmetric encryption, where here is the decryption of the encryption with, you encrypt the public key and you decrypt with the secret key. And for the signatures, the other around, you check, you sign with the secret key, the secret signing key, and you verify with VK, the verification key. Notice that's the type check, because check sign was taking SV key, which is the type for verification key, and V key takes a signing secret key and return a signing verification. Okay. So that's a standard way to represent the equations. So notice here that I made a small difference. There's a small difference here, is that we have equation here, and here we have reduc, and here there's no dot. So basically here what it means is that this is one declaration, whether here the declaration are separated. So there is in ProVerif, there's a slight difference between equational theory and basically right rule. So when it is in this format, check sign is called a destructor. I'm not sure if my accent is good here, but it's basically doesn't act as a, so all the function symbol that you can respond are function symbol that you can that produce an actual message all the time. It's like consistently, no matter the argument you give, it will return something. whether when you declare with a destructor, you can think of this as an algorithm that's modified message, but that can fail. So it will output, it can output something. So here it output X. But if you give, for example, if you give to check sign something that doesn't match that equation, basically it means it will fail, meaning it's as if you're trying to sign with the wrong key, and then the function, the algorithm check sign does not produce anything. So it's kind of the way you can express fails. So of course, instead of writing reduc, you could, to model the same thing, you could say, oh, I'm gonna create a constant fail. Let's say bit string, and no, I'm gonna say something that will not work here. No, never mind. I will come back. I was going to do something, but it's in the development branch. I'll tell to you right now. Yeah, because in fact, to get this tutorial, right at the last minute, I forgot that I was working on the development branch. I was like, oops, that's not available. So I need to verify that my code works in the current one, which hopefully worked. But it worked. I was happy. Okay. So just to give you, just to give you difference between equation theory and right rules. So rewrite rules, so the reduc. The good thing is that it's much more efficient than equation theory because you have this fail case. Basically, when you do, if you write, if you find it is declared not as a reduc but as an equation, if you, for example, write decryption of A by K, even though it's not, it's technically not possible, you may have an algorithm that just will return garbage. So it's not, doesn't decrypt anything, it returns garbage. But it means that still ProVerif will have to consider this term because it's something that your algorithm return if you declare DEG as a decryption, as an equation. But if you declare it as a reduc, then basically this will never be sent over the network because your protocol will just stop. So there's less stuff to consider, so it's more efficient. And also the good thing about reduc is that also it allows you to do some interesting things with this otherwise operator. The otherwise operator, basically, it tells you, it kind of allows you to make several declarations in sequence and say, okay, my algorithm, the output, it will first test, it will first try to match the first declaration. If the argument that you gave matched the first declaration, it will return the element on the right. And if it doesn't match what you gave in as a first declaration, it will try the next one. And you can combine like this several otherwise and make a list of otherwise. So it's very practical, especially when you want to weaken your cryptographic primitives. I told you that, oh yes, we abstract, we assume the cryptographic perfect. That's usually the speech that we give when we present symmetric models. But nowadays, we are trying also to weaken the cryptographic primitives to try to see if our protocol are still secure if you don't use the latest cryptographic primitive available, like an old hash function or something like this. Okay. So here, really to give you a quick, this one is not really a cryptographic primitives, but just to intuitive way of representing what it does. So here, it's a way of representing the if and else test, where you're saying that the first argument should be the condition, and then that's the result of the then branch, the result of the else branch. And you would say, oh, if you have the if then else, then if the first argument is actually true, then it will output, it will be equal to x. And if it otherwise, it will output 1. So it's somehow a way to represent this equality within the declarations. Okay. Okay. Good. Small problem with rewrite rules is that it cannot call itself. So in the decryption algorithm. So the standard equation was this one. But there's some algorithm, some symmetric old one, not very secure, but still, where you also had this property that would hold. So basically, if you try to decrypt something that was not necessarily it was a cipher, but not necessarily from the encrypted is Y, and you re-encrypt that the blurb that's let's say the garbage that the decryption gave you, but you re-encrypt with exactly the same key that you try to decrypt, it will still produce the cipher. So there was some, don't remember the names, but there's some old algorithm that would have that property. And this you can write it with equational theory, but not with rewrite rules. Because here, you would have that your rewrite rules declare it, and you need at the same time to use it as argument. And this is not allowed with rewrite rules. So in the rewrite rules, when you're declaring it, basically the top symbol the element that you're declaring should only appear as top symbol. And there is another problem with rewrite rules, which is that you can't express every algebraic property with them. And for example, so this is I forgot that I wrote it here. Okay, so I didn't need to write it here, but it's fine. But you cannot express, for example, the standard diffie map or associated commutativity and something like that. So there's limitation, but if basically my point is that if you can write it as a rewrite rule and it's good to have a fail, do it. Okay. Again, I already mentioned this. Okay. So now let's see how we model roles. Like what we were working with this. So now how do we actually model the protocol? Okay. So in ProVerif, basically, so here I added already some declarations. So I put a channel, which is basically here represents the public channel on which we're going to exchange messages. So you can declare a private channel if you want. But of course, so you can declare multiple channels, some of them private. Let's assume, for example, that you assume that your participant already share TLS, made a TLS connection beforehand. Instead of modeling it through TLS, you can assume they have a private channel that is not accessible to the actor. Otherwise, you put it as a public. You can declare, let's say here it's my secret that I've declared private. So it's private from the point of view of the hacker, but as I said, it's private to the hacker, but the hacker doesn't know initially as. And those are the type commenter that I was mentioning to switch from one type to the other. And here is the example. So let me keep the role on the side, open to the side, so that we can keep the description here. Okay. So basically, when we describe the role, you really need to describe the role as, okay, let's look at the role. What is the program that the initiator will run? So here the initiator is Alice. And we're going to write the program. What is the initiator that, what is the program that the receiver, so here above in my info description, will run? Okay. So from the point of view of Alice, the first thing, so the initiator, the first thing she has to do is to generate the fresh key. So this operator new, so new key, new K, that represents the fact that we are creating a random key. Then we write exactly what it's supposed to do. So here it says we have to sign the key. So we are signing the key with the secret key, the secret signing key. So here, when you write your process, you can give it arguments. Oops. Okay. And then the first operation that is done, so the first line is supposed to output the encryption with the public key of Bob. So we use the keyword out, so outputs on the public channel, and this is the message that is outputted. Okay. Good. And then, but we need to do the whole role. So now we need to see after this, there's a second part. On the second part, from the point of view of Alice, that she's waiting to receive an encryption from Bob, normally, that should be encrypted with the key that she received. So we are inputting on the channel, C. And here, this is the value that we will receive. We don't know exactly what is the value currently, but we should receive some value, and we will decrypt that message. So it should be a cipher normally. Decrypt that message with the key K. Okay. So here we put the type again. Here we put the type here with X S cipher. It doesn't mean that the attacker will only be able to give a cipher. Here the typing is only to help you for your model, meaning that the attacker, because he has control over the network, will be able to send you a pair, for example. And so in that case, X will be a pair, and so you need to also consider the fact that maybe you will not receive an actual cipher. So here 0 means terminate, basically, nothing else. But of course, normally you should have the remaining of the protocol plugged in cycle with something. And then you have the same as on the receiver side. If you ever plan to use ProVerif, I suggest, I usually don't like to make advertisement, but you can use Emacs for syntactic coloring. But if you use VS Code, a colleague from Nancy developed, I think, one of an extension of VS Code that basically allows you to, while you type check and tells you the error to avoid to run the tool and read, so it's much nicer to read. So for example, here it tells me that I'm expecting only 2 arguments of type signature and SV key, but I gave you a bit string, so I forgot to cast. My signature because PD crypt was returning basically a bit string. So here I should do Okay. So this tells me basically, oh, I'm expecting giving here a signature, but I'm casting it. So now C has become of the current type, and here I have the same thing. Key is not check sign. It should be. And then there's no more errors. So you know that so far we've done well. So if you want to run this on ProVerif right now, it's completely fine. So let me see. Oops. Now, why do you switch? Then you run it here. So I think we were on the 5, step 3. Forgot to register. Okay. So here right now, the output is null because it tells us how your process is, there's nothing in it, and there's a reason for this. Is that right now we just declared the function, the program, but the main system, you need to tell him how to use your function. So right now the main system is 0. So once you indicated, well, the role of the initiator and the receiver, you also need to describe how you're going to use them. What is the scenario that you're modeling? And that's also very important. So let's go into the system. Here. Okay. So for example, here we have a system where we're saying, okay, we're going to just model 2 agents with an unbounded number of sessions. And so if you have 2 agents, it means that I need to create technically I was going to create 2 different keys for each participant. But since only Alice is signing, so I'm creating 1 signing key for Alice, one encryption key for Bob, okay? And generate the public key. I give the attacker, because it's important also to give information to the attacker what's supposed to be public. So I give to the attacker the verification key of Alice and the public key of Bob, because he has the right to use them. And then I run the two roles in parallel. So here this little line indicates that the two processes are run concurrently. So, and this exclamation point here represents the fact that it's basically multiple copy of the same process. So by writing this is the same as basically writing this, and so on and so forth. Okay, and this for unbounded number of time. So ideally, what you would like to do is, well, not just two agents and unbounded number of sessions. You would like to have unbounded number of agents, unbounded number of sessions, each talking to each other. You want to really represent the full model to be sure that you're covering the whole case. Okay, but one thing that I didn't mention is the security properties. So I gave you at the beginning of the talk, what time is it? I have until
11:30.
Okay. So at the beginning of the talk, I gave you like a vast array of security properties, but in fact, in principles, there's basically two different kinds of security property that ProVerif can handle. There's the reachability kind, which is basically is going to try to, no matter the action of the attacker, the system cannot reach a bad event somehow. So we use this to represent authentication and secrecy, for secrecy as well. And you can represent malleability works well also. And you also have equivalence properties, like basically anonymity, vote privacy, and linkability, because this you can't express them as a reachability property. Let me give you an example of the vote privacy, because this is usually the one I like. So in the secrecy, it's really, okay, I generated a secret, and you want to see if the attacker is able to deduce the value, the secret itself, S. But in the voting system, if it's a referendum, and it's yes or no, the value of the vote is known, it's public, it's yes or it's no. So the fact that the attacker knows yes or no, he knows them. That's not a question. What he doesn't know is which one you choose. And so this is where we use the notion of equivalence. So if I have time, I will talk a bit more about it. I think I will, because I already wait. Yeah, so internally there's, internally there is a semantic, within the model, but I mean, most of it is fairly intuitive, so it's very hard in the academic papers. But unfortunately, sometimes it's a bit necessary if you want to, especially if you want to improve the tool, but you want to be sure that what you're using, what you're modeling is correct. But basically, for instance, as mentioned, for secrecy is that every state, so we have a transition system that basically describes how, with respect to how the system evolves, how you could probably evolve, depending on the action of the attacker. And what ProVerif will verify is that no matter the sequence of action that the attacker can do, so if your state your protocol reach some state, here let's say configuration CN, you want to ensure that no matter which sequence of transition that your intro system can do, the secret key, K, for instance, is not deducible from the attacker knowledge in the final state. And ProVerif will be able to verify that kind of property. So this problem is undecidable in general, meaning that for unbounded number of sessions, meaning that ProVerif may tell you yes, it may tell you no, but no and give you an attack. But it may also either not terminate or tell you it cannot be proved. So it cannot be proved is kind of bothering because you don't know if it's yes or if it's no. Still better than not terminating because, well, it really doesn't give you any information. But the cannot be proved just say that because ProVerif does some abstraction, he tried to prove technique and he didn't manage to prove, but he also didn't manage to reconstruct from his internal state a correct attack. So here, if you know how ProVerif works internally, you can sometimes help him and give you some slide at the end. Okay, so how do we model this? Can go back to the there. So here I'm only looking at correspondence properties, reachability properties. So this is, for instance, how you declare that you want to show a query, and here you say attacker of S. So this is equivalent to attacker of else implies false. Okay, so it's really, if the attacker knows S, then that should be false. But you may have, for authentication property, you may want to say, oh, if the receiver finished, and it was verification, because basically here there's no identity of Alice and Bob, they are identified by their key. If the session finished, because I put an event here, so events are basically in the syntax, they don't interfere with the protocol. Then you just use them to model your security properties. So in terms of your RFC or in your security models, adding an event does not modify the behavior protocol. You just put events at different places in the protocol to model your security properties. So here we place one event to represent how the initiation started with, well, the verification key of Alice, the public key of Bob, and this is the secret key K that was generated. And we also have an event that represents basically when the system finished. That says, oh, the system finished with the secret verification key, the signing key of the verification key of Alice and the public key of Bob. And again, with the key K that Bob potentially received. And you want to be sure that when this is executed, that the key that he received is actually the one that the initiator generated here. Okay. And this is how we model this kind of authentication. You would say if the session finished with the key K, then it must have started by the initiator with exactly the same key K. So here you can think of it, even though it's not written, that we will add it fairly soon. It's the same as here putting a for all, for all blah blah blah, even if it's not false, but just right now it's not allowed in the syntax. Okay. Questions, fun? Good. And so this, well, we could try to see now what this one looks like. So we were in the main system. So already step 5 main system. Okay. So when you run this on ProVerif, let me zoom in a bit. Is it better this way? Yeah. Okay. So it shows you the protocol that you ran from your file, just to be sure it displayed to you, just to be sure that, it's sometimes laborious to read this, but it's a good sanity check to see if, if it's not misinterpreted, especially if you're missing parentheses or something like this. So it's good to have a look if it looks correct. Then it does some, it's a bit verbose, unfortunately. It does some modifications. So basically, it tells you the kind of modifications. So I move the let forward and downwards. So basically, it's trying, for efficiency purposes, when you made a let in your protocol, when it can put them a bit downward in your code, or if you can kind of completely remove them, it does it. So it doesn't remove it, but it's put it after the new. It's not, doesn't really matter for you, but it shows you every time each operation is. And then it starts the different query and basically give you the result, it's true and it's true. So there's some, so here we don't say it, here just say completing. So here the completing doesn't say as much because the protocol is so simple that it terminates instantly. But if it's a large protocol, you will have more information. And you also have information here, which is this goal reachable. So this is basically, and we'll have to discuss about it a bit later because it's due internally have a ProVerif model of the protocol. It uses the notion of home clauses. I don't know if you're familiar with home clauses. And so basically home clauses is just, you can think of it as an statement. The side on the left of the arrow represents the hypothesis, and this is the conclusion. So it basically tells you, oh, if this happened, then I know that this happened. So, and basically it's reaching some, it's done some abstraction, ProVerif transform the protocol into own clauses, simplifies them, and then verify the query on those clauses. And here it works, but I will mention this later. So you have a summary at the end that just summarize what you've done. Of course, something that I mentioned earlier is that what you put in your main system is kind of the most important part. Because here we only did for 2 agents, and basically this protocol is insecure. It's not a good protocol. Despite the fact that protocol tells you is secure. It's because the scenario that you consider is basically too restrictive. You only consider 2 agents. You also consider that none of the agents is corrupt, or the attacker cannot participate in the protocol. So all those information are not there. So we need to give that information to ProVerif outcome. Also, something that happens quite often is that we write a model with, well, here it's only 5 lines, so it's fine. But we write a model, we are happy, and we run it, we have a security proof for it, and it's truly like great. And then when you analyze a bit more, you realize, in fact, you made a mistake in the model, and basically, even without an attacker, the protocol will not run. And if it corresponds to it like this, if it's like, if F finish can start, if finish can never be reached, the property is still true, because it's an else, okay? So it's very important when you model, and I cannot emphasize this enough, even me, I know ProVerif very well, I always put sanity check, massive number of sanity check. In the work that I've done in ECH with TLS, I had like something like 100 training query of sanity check just to be sure that the protocol was 6,000 line. So I could not rely on just my intuition that it would be correct. Okay, and sanity check are fairly simple. You just make events and you're saying, okay, let's see if I can reach the end of the initiator, and let's see if I can reach the end of the receiver potentially. You know, just this and sanity check are these quite good. Like, can I execute the protocol? So if you run this, thank God, it tells us false. Okay, and that's what you want. You want that your basically sanity check are false. Because here the query is, it's the negations, you know, when you write query sanity, event sanity, the same as equivalent to this. Okay. So you want this query to be false because it implies that I was able to reach the event in questions. Okay. And so here suddenly the output of ProVerif is a bit more verbose. So you still have this, you know, this completing, blah, blah, blah. And then you have, give you a derivation, it's a goal reachable, I managed to reach sanity. It describes you the attack in a kind of a weird way, which is like, okay, it gives you step by step. And then after that, say, more detailed output of trace is available, okay? But then give you that kind of trace here. So what it means, in fact, here is that internally, ProVerif, when he's, because he's working with own classes, is trying because it transformed the protocol into own class, is trying to find a derivation of the fact events sanity are. And here is basically describing you the derivation in terms of own classes. And once it has this, so it cannot prove the protocol, the security, but then there's another process that, okay, now if I start from my actual protocol, where I didn't do any abstraction, can I actually make a step-by-step attack? And here is able to do it. So it's a bit difficult to read. So let me see if I can. So to read it, you need to start from your protocol process. Yeah. So basically here what it does is that it's telling you step by step what it's doing. So here the one, each number here in brackets represents the line in your initial protocol. Okay? And it tells you the execution, the element that is executed and the output. So here it tells you, okay, I'm supposed to generate the new silent key. So yes, I'm generating one. And because every time you execute needs to be fresh, it will create a new one, which is different from everything that was created so far. And then you're executing, it tells you, okay, I output the file. So it doesn't display every single line by line. For example, the evaluation, it doesn't display it, you have to do it by yourself. Outputs, and then it tells you what's going on, and you can follow like this. So when you have in copy A, it's basically represent the fact that here you have this unbounded number of sessions. So what ProVerif does is it tells you, okay, I'm gonna create a copy of all the protocol here. I'm gonna call this copy A, and when I refer to the line in question, line A, I'm referring to a specific copy. So if you need to unfold the second time the protocol, it will be another copy A prime, something like this. So just because it's a bit sometimes difficult to read, but it's important because you can actually see what the attack is. Here it's not really an attack, it's a sanity check. You have the ability to have an HTML output. So so in your command, you put the dash HTML with the folder where you put quits, always in the desktop. And then you run the protocol again, which was, step, I think it was 10? No, it was 5. No, 6. Okay, so here suddenly it test levels, we don't have all this blah blah blah. But yeah. Now, in your folder, it created a lot of HTML page. You find the index, and it kind of have a bit more readable interface. When it summarizes again the code and see it again. It also tells you the clause that I told you that ProVerif abstract the protocol into own clauses. It shows you all the clause that was generated. So there's a bunch of them, but all of them is already described and says, oh, the attacker may send the attacker, the message may be sent to the attacker at 6, and so on and so forth. But more interestingly for us is that if you look at the queries, and the one where there is an attack, like for example this one, so you have the derivation, like the close derivation, not very interesting. But you do have an attack graph. So it's a bit more readable because here you can see how it works. Kind of says, okay, you have the honest process. You see what is sent to the attacker. It tells you how many times it's unfolded. So it unfolds. It kind of shows you in the Alice and Bug form your attack. So it's a bit easier to follow. For small protocol, it works well. When you have a very large protocol, it can be a bit massive. So I use it on small protocol. I usually have the tendency to keep on the command line when I'm working on very large protocol, because otherwise the PDF becomes humongous, and like Safari or Firefox kind of crash most of the time. Not so great. Okay, but for at least if you want to try ProVerif, it's a very good way to see that your system works. Okay, so yeah. let's move a bit forwards, and I want to tell you, So I wanted to tell you that I told you that this protocol was not secure. And of course, one way to make the query false, like even the authentication query false, the one that we are trying to prove, is if you suddenly let the attacker participate, then of course that should not hold. If the attacker participates, one way of making the attacker participate, so I'm going to create a new key, let's say for an agent C, and I'm going to, instead of outputting the public part of the key, I'm outputting the secret key. So it's basically you're giving to the attacker a fresh key, and you're telling to the initiator, so the initiator is still honest. So when you model the protocol, you only model the honest part. Never try to model the attacker, because basically ProVerif does that for you. So never try to model the attacker part, because you will even confuse the ProVerif, because you will think, okay, that's supposed to be honest, but then everything's public, so it's kind of confused. So only keep to the honest protocol. So here you have an honest protocol, Alice, that is basically willing to, that want to discuss to the attacker. And here we are still Bob, that basically is still waiting to talk with Alice. And if you run this, you would have an attack. Okay? You can have a look at it. But already you can see that, okay, now it's become complicated, because we need to understand how do we model to make this consistent, because we want maybe to try the attacker would like to talk to Alice, we would like the attacker to also play the role of the receiver, and maybe the same agent could be at the same time initiator and receiver, because you have all those scenarios. So there's many different ways of doing this, and I'm going to show you the way after many iterations. And now the way I always do, I think it's kind of it's very practical. This one. Okay. One way of doing so is to use tables. So far in the semantic of ProVerif, I only showed you input, output, if then else, let's, and select. But there is something that is available in ProVerif that is a global table. So it's basically a global memory. So you can, it's like databases if you want. You can create the databases. So here I'm creating the databases of agents of keys. And so those tables, the honest participants will be able to have access to them. It's like a magic database that is shared with every participant. But the attacker do not have access to them. If you want to give access to the attacker, you need to make it interface with on a public channel. Let me show you. So when you declare tables, this is the name of the table, this is the argument. So basically here is a database where each entry is composed of a quadruple with the secret key, signing key, the secret verification key, the secret encryption key, and the secret authentication key, and the public key associated to it. And here we can define, actually generate a lot of different agents. So I'm gonna have a process that I will say, okay, this is my process to generate my agents. I'm gonna put a bang in front of it, verification, to say I want to be able to create as many agents as I want. And for each of them, I create the new private informations. I'll put the public informations, and I will record this information inside the table. So this insert is what, every time you do an insert, it will be recorded inside the table. And then I also added an event compromise. And after the compromise, I put the private key, I outputted the private key of the agents to the attacker. So this bit here, right now, let's ignore it. I'm gonna come back to it in a few minutes. But we will use it to actually allow modeling corruption of keys, okay, and how to express your security property in a nicer way to allow compromised keys. Okay, and now when you want to run your initiator, run your receiver, instead of generating the keys and blah, 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 because they are already, this process will deal with this, you just need to retrieve from the table, say, okay, get me from the table an entry, and I'm going to take here the signing key, I'm calling A, and give me another entry from the table, potentially the same. So every time you do a get, it will try to get one entry from the table, like any entry of the table. So you can do tests. Here, if you don't put any test, it will take any entry and associated variables. But if, I don't know, imagine that you had a public secret key that already existed, you can make some tests with the equal symbol. So here it tells you, oh, but that guy doesn't exist anymore, and it doesn't exist, so please declare it before. Imagine that it was declared, you could actually, and here you would only get an entry, let's say Y, an entry where the first element is that particular element, and then this Y will be associated. Okay? The good thing with the table is that it can be done multiple times, in the sense that if you run several times the get, it will basically, as long as there's one element in the table, it will be executed. So it's basically a selection within a set. Okay. And then you can use this for the initiator, you use this for the receiver, and then you can run your main systems. And with this, you have covered unbundling above session, unbundling above agents, with potentially whoever talks with each other. We have covered all the possible scenarios that you want in a fairly small and elegant way. So, what about this compromise key? Because here, if you run, okay, imagine that this was not taken. I already give the, so imagine that this part was not here, it's hidden. Okay. If you run the query, that query says, oh, the attacker, imagine I have this. Okay. If I have the attacker, if the attacker knows S and that S was the secret message that was generated by the receiver, okay, this should be false. Here it expresses the fact that the message S that was created by the nonce S that was created by the receiver should always be secret from the point of view of the attacker. Okay? Because it's saying, oh, if I reach S and the secret, then it should be false. But of course, now that we have compromised keys, of course, this is possible because the attacker can just run the protocol up to the end, obtain the key, decipher, and everything is on. But what you actually want, you can amend your query and says, okay, here's if the attacker knows the secret key that was generated by the receiver, so this one, then it means that either the key of the receiver has been compromised, or the keys of Alice have been compromised. And here suddenly it becomes kind of a good property because, okay, my protocol only ensures the security if you don't compromise the keys. But the good way is that here it's not as if you're compromising everything or nothing. You're really specifically, this scenario means that even if you have multiple sessions in parallel, and many sessions are compromised, but you yourself, you know that you and your partner are not compromised, then you know that if that query is true, then you know it will be secure. That's the way to mix compromised scenario with non-compromised scenario. Okay, if you run this, unfortunately, that's why this is not a good protocol, you will have you run it here. This is, yep, project file. One project in second. Okay. And here give us an attack, okay, which is basically just a man-in-the-middle attack, very standard, where Alice will want to talk to the same as the scenario before. Alice wants to talk to Charlie. Charlie will be able to decrypt and re-encrypt the key of Bob, send you to Bob, and then you will have an attack. So it's very classical man-in-the-middle attack. But that's why it's important to correctly model your scenarios in a very large way, because otherwise you miss basic attacks. Okay. So let me go back quickly. So that's it for the example with the dealing cycle. I told you that, okay, so far I showed you kind of a very classical equation theory, but it was ProVerif you can do more complicated things. So who knows Merkle trees? Okay, great. So I'm still going to explain a bit, but so Merkle tree is basically a very useful data structure in quite many protocols, and it basically acts as a tree of where the label are hashes. And basically, if you can see here, so the root of your tree is what we call a digest. Okay, you can see from the ledger, and each node is basically the hash of the left child with the right child, and you can build like this. The good thing with the Merkle tree is just to give you the brief summary. So all the data, yeah, that you store in the leaves. And that it's an append-only structure. So if you want to have a public ledger, you can use Merkle tree. And the good thing is that you can make proof of presence of an element in size logarithmic in the number of data. Same thing for proof of extension. So it's useful. It's useful when it was used, for example, one of the first usage, maybe not, I don't know if it was the first, but the first time I seen used was in the certificate transparency when Google created by Google with for PKI infrastructure. It was used also before, but I don't know any other cryptographic protocol before that. And the important thing is that it's because it's logarithmic, you may have a lot of data and still keep the proof, and those proofs are the ones that you want to send over the network. And the problem is that here suddenly what the proof looks like and how to verify the proof, it's become much more complicated to express this as an equational theory, or even it's even impossible. With an equational theory, you could probably do it, but it's definitely something that ProVerif or even any other tool will not be able to do. As an equational theory, the standard technique we do. But with ProVerif, we have another tool that allows you to do this. It's basically all clauses. So I'm going to give you a bit. So what is a proof of presence? For example, imagine if you want to prove the presence of D2 in the digest, but you basically give to as part of the proof, the data, the sibling node in the path, as well as the path in question where your data is. And from this, you can reconstruct the origin digest, which allows you to compare basically two hash, and you're able to reconstruct your, you have a guarantee that your element is in your tree. Okay, proof of extension, let's keep it. Okay, so this is something that we can do, but of course, I want to, in one of my recent work, we implemented it. But just to show you how to make it in ProVerif, I make you a more simpler version, which is imagine instead of a Merkle tree that you have just a list structure. So it's suddenly the proof of presence, and it's not logarithmic, it's linear, so it's much less efficient. So of course, it's not something that you would like to implement in reality, but it's simpler to explain. So here the proof of some data, let's say D3, okay, that would be the digest, the rest of the digest after, okay, which would be D4 up to the end, and the previous element, D1, D2. So if you want to verify it, you just need to do, you compute the digest D3 with what you got here, then your hash was D2, then the hash was D1, and you compare with the element that you got, okay? Okay, so now can you model this in ProVerif? Oh, wrong one. This one. So here for this, we're going to use, so I already, so you can define, let's say a structure of list. So you have, we can define constant for nil, list empty, and the constructor, so very normal list construction. And you use a predicate. So the predicate in ProVerif, you can think of it as a function symbol that always returns a Boolean. You take an argument supposed to return a Boolean. But it's not a function that you can use inside a message. It's something that you can only use within ifs and else tests. So if you want to test something, you can use this as a predicate, but you cannot send over a network the value of the predicate, because anyway, it's only going to be true or false. Okay, and here that would be the proof of presence. So we want to get a proof of presence. We want to get the elements and we want to get the digest. And basically we want our predicate should hold if and only if the proof of presence actually is a correct proof that the element X is inside the digest the third element. Okay, so here we have the function for the zero digest plus our hash function that will take the element that you want to the data, the digest, and return another digest. Okay. And I declare also function PP for the proof of presence that will take, as I mentioned, the value of the list of the previous elements plus the tail digest. Remember, it was in the tail plus the list of elements. And here you can use this clause here. That's the key part. Okay, so this is exactly basically an on clauses. So you express the semantic of your predicate using using on clauses. It's again is this if then statement. So here it says for all xd. So here this is basically the same as no hypothesis implies my predicate. So it's the same as saying this always hold for every x and d. So if you think about it, if you give a proof that contains the empty list and the digest d, then and you give x and the final digest is hash of xd, then yes, then in that case the proof with the empty list and d as digest is a correct proof that h is in this final element here. Okay. And here you can do basically definition by induction, because you're saying, okay, if you have a proof of proof of presence of x inside a big digest, d big, and that is the proof, the correct proof for x being in d big, then basically you can, from this, you can construct a proof of x in another greater digest, which is here now is h, the hash of y with the bigger digest. And now the new proof is you concatenate y, the previous element, with the list that you used in the previous proof. Okay? So you can do this kind of declaration, and that's the semantic is that every term, every predicate, instead of predicate that is derivable by this set of on clauses correspond to the semantic of the predicate. And here you can, with this, you can actually make some, let me start with those. You can make some nice queries. For instance, you can say, okay, if it is, if you have proof of extension and proof of presence, so you should have that, for example, if you have a proof of presence of x inside the digest D1, and you have a proof of extension of D1 to D2, then there must exist somewhere a proof P2 of x inside that greater digest D2. Okay. So here, this is where, this is historical notation. So again, it's gonna change hopefully soon. So here, when you in the query, when you declare your variables, the quantification is as follows. So the variables here, there's no for all. It's not a for all, it's a for all that exists. So basically, here you just declare all the variables that appear in your query. And the quantification is that all the variables that appears here are quantified universally. And all the remaining variables here are quantified existentially. So if I rephrase this in a more logical way, that would be basically for all, let me see if I'm not mistaken, this one, but not this one, and this one, there. For all blah, 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 exists, P2, okay. So hopefully soon you will be able to write query like this, which is exactly syntactically the same as this, but historically, the ProVerif has been developed for more than 20 years. So there's a lot of cleanup that needs to be done, basically, that are leftovers from old initial implementations. Okay, So, and so here, if you run this, because probably it's magical, will obviously, oh, yeah. Okay, something that I forgot to mention. So here in this file, you only have just the queries, okay? And suddenly the declaration that I gave you before was in this other file here. So that's something that you can do in ProVerif because, you know, like in the Linux code, it's a very tight, small example, so everything fits into one file, that's fine, that's cute. But when we have large protocol, everything in one file is not reasonable. So you can create basically libraries. So if you are PVL, it's basically the extension of your libraries. And so when you call ProVerif, you can put lib hash list, I think it's step 1. I don't know why I have to. It's step 2, let's say. And then your final query that contains your query. So as I told you, ProVerif magical, so it gives you a canonical proof. But it's not able to prove it directly. And here there is a reason for why it's not able to prove it. So the problem is that the clause here in our definitions it's by inductions. Okay? And so the way ProVerif works in this resolution is that it has its own clauses, and it will try to basically like if he's trying to achieve this guy, but he's going to say, okay, if I want to achieve this guy, this and this I need to deduce it somewhere. But this fact can be instantiated using the same rule again. So by using this rule, it's just you're basically instantiating having a fact which is greater and greater and greater and greater list, and you can keep like this for forever. So ProVerif realized that this would loop, so it basically doesn't stop, but it's making some in the resolution is that at some points it will basically block and tells you, okay, here I will not continue for this. I will block in my resolution and will stop. So if he's able to continue, then good for him. Otherwise, he may obtain, that's one of the reasons why he may obtain a candidate. But again, I will explain this if I have time a bit later. But what is important is that because this is basically a definition by induction, we also implemented in ProVerif a way to do proof by inductions. So it basically is trying to prove a proof by induction on the size of your execution of the final trace. So it's going to prove really saying, okay, let's try to prove for every execution of size n, not every n step, assuming that my query holds for all the trace of size n-1 or less. And for this, thanks to this, if you do this, and if you put this induction at the end of your query, it is able to prove your queries. So that can be useful, and in fact, if you think I gave you like this Merkle tree definitions, this is something that was published in your recipe, which is basically the clause that you use to represent the predicate, the proof of presence in the Merkle tree, and a proof of presence in a proof of extension also in the Merkle tree. So as you can see, it's a bit more, because the data structure of Merkle tree is much more complicated than the hash list, it's more involved, but you can do it. Okay, much more late than I thought. Okay, so let me, okay, so before I show you a signal, I wanted to make a fundamental fact about ProVerif and its calculus is that it's stateless. So normally when you use, and you only have output on channel, input on channel, is and else. You can do some evaluation, but that's basically it. So, but you have a lot of protocols where each participant is supposed to have variables that contain the state that is updated. For example, in TLS you have this, in signals you also have this, where it's recalled the number of keys that have been used or something like this. So we've seen the tables that you can use as global memory, but it has the tables in ProVerif has some problems that you can't delete anything in a table. Once you insert something in a table, it remains there forever, because you can't delete inside the table of ProVerif. The good thing is that we have private channels, okay? And so in fact, we can model with private channel any state that we want. It's a bit involved, but you can do it. So think of a state. I'm giving you the translation like the Occam's style, or where you have your reference that is initialized. So that would be the reference or your pointer if you want. And so in the camel, the reading is done with the exclamation operation, and the writing is done with that symbol here. Okay, so we would like to model something like this. But something that we can do, in fact, is we can create a private cell and use this cell as a state. So why does it work? So, like this. So the initialization is basically outputting the cell the initial value. Reading will be you read on the cell and you just output right after exactly the value, basically read and write. And writing is that you basically read on your channel and basically output the new value. So why does this model states on like a cell? The key part here is that the communication in the model behind ProVerif is synchronous. So far we've only done communication between on the public channel. So it's basically you communicate with the attacker. So this is ProVerif takes care of this, and so it's basically either way. But when it's on a private channel, and in fact, normally on a public channel is the same, is that to be able to output on channel, you need to have a receiver that is there ready to listen. You can't, there's no buffer. You can't just output on channel and then continue, and then someone else will later on read. Is that if you're trying to output and no one is reading, then you're blocked. You have to wait until someone is reading. And so the good thing now is that now, if we think of the use cell, now imagine that you put those operations in parallel. X, now it's cell N, okay? In parallel with input cell X. Let's say N1, N2. Okay. So imagine that you have this three small processes in parallel. Basically, the output here, because the communication is synchronous, it can only interact either with this one or this one. Okay. And once an output is done, an output cannot be sent to two inputs simultaneously. It's really one input with one output. So let's say that this on this private input is done with this one. So let's say that communication is done with this. So at this moment, this disappears and X becomes 0. So this disappears. So now it remains a process where you have output cell N2. And here you have again input cell X and input cell N1. So of course here you can have this guy that is this one. So now X will be equal to N2. And after this, well, keep outputting. So basically when you do this cell modeling, there's at any moment, at any given time, there is only one possible output available directly at top level. And that output available, the content of this output, represent the current value of your cell. Because basically, for example, if this one was not eaten, you cannot execute this before the input is done, meaning before you're having access to the cell. So this is usually the part that is quite tricky to manipulate, but it's very useful and to be able to model most of the standard program. So that's basically what explained here. Okay, and the good thing also is that by doing exactly the same mechanism, you can represent basically locks and locking mechanism. Because here I just put input and out followed directly by an output. But imagine that now between the input and the output, you put other stuff inside the process. It means that it will basically act as a locking mechanism where the input is you have a lock on your cell and you read the value, then meaning that any other process that is put in parallel will not be able to execute, so they can't access the lock. And you release the lock when you write on the cell. Okay? So the output represents basically a write and a non. And so here, for example, the sequence of events A, B, and C would not be possible because A would need to be executed here. Then B cannot be executed because there's no more output available because the output here will be eaten by this one. So at that moment, there's no output to be executed with B. And so you must have A, C, B or B, A, C, but not A, B, C. So just to give you a very small example, that is very simple, yeah?
Is there a library that encapsulates these primitives?
There is not natively yet in ProVerif, but there is a front end of ProVerif that's called Cheval. That's so it does not allow you to have this write. You can write. You still need to write yourself the in and out, but Cheval allows you to help ProVerif because this kind of memory cell semantically it's handled by ProVerif, but in practice, without help, ProVerif suffers a lot, struggles a lot. And it's only recently, since 2018, that ProVerif has been able to correctly handle that kind of scenario using axioms and lemmas, but I'm going to discuss about this a bit later. And so this is the front-end JS that can be useful for that. Okay, so here give you the simplified YubiKey protocol, where basically you have a YubiKey was to kind of those little things where you can click and activate every time you want to authenticate. And very simplified, you have basically the YubiKey here represented by Q, the process Q, has a state that every time you click, increment the value and encrypt that the current value, or it should be a small I here, with some shell to the server. And the server basically you wait for an encryption. You will receive an encryption, check the current value of his cell, decrypt, look at the value, compare whether or not that value is greater than the cell that he had before, but the current value of his cell to be sure that there is no replace. And if it does, then it accepts and update the value of the cell, and otherwise just don't accept and keep the state as it was. So of course the real YubiKey is much more complicated than this, but that's a very simplified version. This is how you could use states in ProVerif. Okay. Any other question on this? Okay. So far I've shown you really simplified version. So now let's look at the double ratchet. So this is the double ratchet. It's something that in fact is not yet. I mean, the double ratchet itself is yet already published, but the analysis of it. It's not yet done. So it's something that I'm currently doing with a colleague. So I'm showing you, I know it's recorded, but it's a preview of what the model will look like. So if you look at the nice thing about the raw ratchets, compared to the NFC of TLS, it's like quite different. It's well presented. There's a lot of graphic. It explains you the protocol, what it's supposed to do. So it's really great. It's a very nice. If you want to have a have a go of a protocol, real life protocol that you want to model in ProVerif. The work that has been done by the senior in the explanations, not just the ratchet, also it's yeah, thanks. The protocol on top of it, I forgot the name. X3DH. Yeah, it's also very well explained. So I suggest that you have a look. So it explains you how it's supposed to work, the security property, and blah 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 blah. So all of these are great, and it's good to understand. Wait, maybe I can ask, who have never heard of the double ratchets or signal? Everyone has heard? Perfect. Okay. So it's basically, it's a way to, but it's in signal. So it's a way to generate constant, every time you want to send message or receive message, it's basically a technique to ensure that every time you encrypt, it's a generation of key that ensure that you're always basically using a key one time for every message that you send or every message that you receive. Okay. So it's kind of use a lot of KDF. So I can maybe show you this. So imagine that you have Alice and Bob here. Okay, that I want to discuss. So they share originally some Bob has some public key that he can send to Alice. Then Alice can generate the on private key and public key, make some kind of a Diffie-Hellman operational nets, which will generate a Diffie-Hellman output. And this Diffie-Hellman output will be used once she sends a public key to Bob to obtain, that will be used to generate keys, okay? And then you can keep doing this kind of stuff to always generate something fresh. But at the same time, just to show you, they will use, try to use diagraph here. The small part I showed you was this, but then with the output that generates, they will create some kind of a chain of a root key, and for each root key, they will create sending key that are derived from each other and receiving key that are derived from each other. So basically, all the keys that are generated are somehow rooted, okay, through the complex mechanism that is behind this. So I'm not going to describe fully the signal. That's not the purpose of this tutorial. But just to give you that everything that we've done so far that I've showed you on toy example, you basically do the same thing here. So when I look at it, I read, although to be honest, I haven't read all the explanation or description, because in terms of organization, what really matters to me is what are the cryptographic primitives and what are the role of Alice and Bob. So here, it's very nice because they exactly tell you what is the cryptographic primitive that they're going to use. They don't tell you exactly, the empty curve that they're using or what is exactly the algorithm for the encryption. Doesn't matter because anyway we're abstracting them. So perfect for us. And so here, if we compare with, so we have one called generate DH that's supposed to return a Diffie-Hellman key pair. Like, okay, so let's do this. So I created a crypto, my library for primitive. So I'm saying, okay, Diffie-Hellman. So I'm gonna type the scalar and the point. So here we have the elliptic curve, so it's multiplicative group. And I have the function key pair that represent a pair of the private key and the public key, and the function generate DH that was generated. That generate the key question. So here you can see this let fun here. It's kind of a nice addition. It basically allows you to generate more complex terms. So before the term was just evaluation lets, but the let fun allows you to create 10, you can call this into your protocol, and basically every time you call this, it will execute all the code that you put. So you're not allowed to put everything in it because it's really represent terms. So you can't put output and input on the channels, but you can put generation of nouns, you can put if-then test, you can put events, you can put and even insert of table and retrieval of table. Basically, everything that is hidden from the attacker, not observable from the attacker. And basically here, what we are doing is exactly following the RFC. So we have, here we have a DH that is supposed to basically take a differential pair, take a public key differential and apply, exactly return the output from differential calculation between the private key from the DH pair and the differential public key DH pub. So translation, it's okay. So I have my left pun DH that takes the two arguments that was given to me. I create my key pair, but I don't create. I match. I match my pin and my key pair, because it means it's supposed to be in that particular shape. And I do the multiplication with the private key and the public key as the description tells you. Then you can keep doing this, and so on and so forth. So for example, here for the description, it's a bit more complicated, even though it's symmetric encryption, it's a bit more complicated than the one I showed you before, because now we have 4 arguments. Because in the AEAD encryption algorithm that they mentioned, that they use, you have the plain text, you have the key, so far it's the same, but they also have, sorry, I said 4, it's 3. You also have the associated data, which is, you have to, when you encrypt, you can associate the data, and when you decrypt, you need to also not only have the key, but you also need to know the associated data. And usually that associated data can be public or something to identify, basically. Okay. Meaning that this, well, you need to express what it's supposed to do. So let's say for AED, follow the same thing, encryption, and I do my redact, and decrypt, encrypt, and so on and so forth. Okay. Okay. Now let's look at something that is a bit more complicated, which is this state variables. So here in the state variables, literally this says that every session you should have a state that contains all the information, which is differential, ratchet key pair, a lot of stuff. And something really problematic, which is a dictionary. So not only the state contains normal value, but also contains a set. So for those particular values here, easiest way to do is to use the private channel as I mentioned. So this is the type of our data type for our states. It contains exactly all the information that I mentioned, which is the ratchet key pair, the ratchet public key. So every time when I create something, I try to be as close as possible as the RFC from the explanation. Okay, and then you're going to use it. You're going to use it with a cell. So this will be basically the content of the cell input. Okay. But here, as you can see, I didn't put the set in that particular element. I stopped with PN, which is number of message represented chain, which was this guy here. But there is not that set. Because the problem is that ProVerif does not include a set operation. You can't send sets, so you can't create a set element. You could use potentially, as I mentioned, the list. When I put you a list in the numerical tree where you can have a list with the cons and the nil, but that's something that ProVerif will not manage very well. What you could do, on the other hand, is to use the tables, a combination between the tables and the cells. So basically, the sets, each entry, we will have a table that represents the set of everyone, but inside the entry, we will put the identifier for the particular state. Let me show you. Let's see. There, yes. So basically, we will have a table that will be table mskip, which will exactly correspond to that mskip here. Okay. So it's supposed to contain basically a dictionary with message key indexed by ratchet public key and the message number. So there's 3 elements per entry. Those are the 3 elements in question. And we will, so forget about this right now. And we will also add a session identifier, which basically will be similar to the private channels. So inside our table, we put basically, I could have put the channels to represent itself, meaning that every entry, the semantic of my table will be that every entry that corresponds, that have as first argument the same session info will represent the actual state that is stored inside the signal, inside that dictionary. Okay. So you can really do this combination between the cells with private channels as well as the table. Something that is still problematic here in this representation is that I told you that tables do not allow deletion. Okay? So this is problematic because in Signal, it's clearly written that at some point, basically every time you use the key, you're supposed to delete it. So I think it should be there. Okay. So here we have, so in Signal, they are good enough for they write almost the role itself. So translation from Signal to ProVerif is really not that hard. But here you have a separation which is delete from the states, from the dictionary, this guy. But if you don't have state inside, we don't have deletion inside a table, how do we do this? Well, here's the trick, which is to use what we call, I think, restrictions. So I showed you so far, it looks very much like queries, but it's basically, so it has the same semantic as a query. It tells you, oh, it's a property on a trace. And here it basically tells you, you're adding a restriction, you're saying, when you're proving your query for life, prove on every traces that satisfies these restrictions. So it's a way to, you're basically, in your main model, you're allowing more behavior. So we are using the table by saying, okay, we don't do deletion, that's fine. So we are going to allow you to potentially, in the actual process calculus, use multiple times the same key. But we're going to use a restriction that says that you're not, that says if in the trace you see two events that is exactly the same arguments, and you have this kind of timestamps, and that's basically this event has been generated at that particular timestamp 1 and this one at timestamp 2, then in the restriction, this must be exactly the same timestamp. So this basically guarantees you that you have deleted you haven't reused a key twice, which in other words says you have deleted it, and then after this, it's like as if you never deleted it, but you also guarantee that you've never reused it. So it's the same as if you just forgot it. So it's a very nice trick to represent that kind of complicated scenario with deletion, still using tables. Okay. And here, once you have this, you can actually model the deletion that it is in Signal as well as in session. So in the deletion, you're saying, oh, deleting something inside my table, inside my state, is just, I create a new timestamp and I raise an event mskip there with that particular timestamp. In that once you call delete once, you're never going to be able to call it another time. And inserting the skip state inside the dictionary is just inserting the key inside the table. And here in your function, you should give in which session are you talking about to be sure that you are keeping all this information. And here you're creating a timestamp corresponding to when that entry was. Okay. So working with restriction works well. It's very powerful. It's one of the new features of ProVerif, and it's really, really useful. But it can be very dangerous because you're basically making the model yourself. It's not native. You don't have a native operation, so you need to be careful that your restriction is correct. And for example, here with this scenario, this kind of modelization only works if we are sure that we don't have in our signal, we don't have a behavior that is, for example, I add a key, delete it, then add the same key, then delete it again. Because if you consider a set, let's say that you have, let's say that you do insert key one, then delete key one, then insert key one, and delete key one. Okay. So this in term of signal, the protocol signal, that is a behavior that technically, potentially could be possible. Because every time, signal create keys constantly, delete key constantly, don't use them. So there is a priori no guarantee that it does not regenerate the same key. Normally it's not supposed to, but it's a requirement, it's not something by construction.
But wouldn't it be easier to just say, like, this is an assumption that the keys are always sort of unique, that you don't reuse this, in this case, the ephemeral Diffie-Hellman keys, because you are kind of making that same assumption also with the random numbers. You could say like, oh, I don't.
No, because random number, when you generate a new random number, you can say, okay, this is really internally something that is done on your computer, so the attacker doesn't have access to it. But you could imagine that, oh yes, normally your signal is made, your protocol is made in a way that the key are used once and generated, there is no two key generated twice. But maybe the attacker, by mixing the message or doing something unexpected, is able to actually make you generate twice the same key. Possibly, potentially it's possible, and that could lead to a problem.
Well, I think in my view, it's possible in both cases, but you need to make some assumption, or you could make some assumption to avoid the hassle of sort of dealing with this specific case.
Yes. Okay.
Because so, the same with like in a TLS, let's say TLS 1.3, you're making the assumption that the initial, if you use the public key-based authentication, that there's the key share size changed and the key shares are essentially ephemeral Diffie-Hellman, sort of ephemeral Diffie-Hellman public keys. And so you could say, like, if someone wants to shortcut the whole process, they could just store them and keep them around and then reuse them theoretically.
That's true, but here, for me, there's a difference between. I'm more concerned. I'm assuming that the honest participants are actually doing their job correctly. So if I look at the signal thing here, I'm assuming that, let's say, the ratchet is done properly, so all the keys are generated nicely. So I'm not assuming that the honest user will do a mistake. I'm assuming, oh, maybe the attacker will be able to trick an honest user that will follow correctly the protocol, that will think, oh, I generated this key, which was correctly generated. Then I used it, so I deleted it. And now later on, I follow the protocol, I receive some stuff from the attacker, I generate a new key, and you hope, and if he follows it, maybe the key will be the same. So of course you could say, okay, I'm going to assume that this will never happen, but it weakens your security proof. You could do it, you could weaken it. But if you want to make sure that, basically you could try to prove that that scenario never happened, that the attacker has no way of tricking the honest participants to make it generate in the end twice the same key. So that's kind of different level of security, because one way there is an assumption, as you said, you have a proof with an assumption, but if you don't want to use the assumption, then you need to prove something else. And the proof here is exactly basically what you have in mind, is that kind of scenario, which is you're going to ask ProVerif to say, okay, if I give you twice elements in the tape that was inserted, and that potentially at two timestamp, they need necessarily to be exactly the same timestamp. So meaning that if you're able to prove this, it means that even in the presence of the attacker, if the honest participant follow the protocol, then for sure the key will always be different. No key will be the same, and then your modelization will be correct. That's kind of the. Okay, so I think I already overboard, so I will stop here. So just so we are currently in the process of keep doing, but as you mentioned, as you can see, we do the each protocol, and just I will finish with this. You have this is come from the spec of Signal, where they describe what does the initialization of the ratchet by Alice. So we use basically we are almost copying, mirroring what is in the Signal. We do the same with Bob, and then for each process that is expressed in Signal, we are also making a mirror role. And then we can express our property primitive, and then the hard part is how to make ProVerif prove those properties. But this, unfortunately, I didn't have time to show you that. Thank you for your attention. So I only had the time to show you kind of how to use ProVerif and hopefully model correctly your protocols. So hopefully when you run it, ProVerif will tell you either true or false. If it gives you kind of the proof, you can have a look at the slides. Some part are quite detailed. There's some techniques to how to help ProVerif when he end up in the canopy book, or even help ProVerif when you have the impression that it's not terminating. So there's some trick and tips that are in the slides, so you can have a look. Same thing, I also put some information on how to model equivalence property, because right now we only talked about the utility property. Thank you very much.